everyone. And welcome, everyone. Happy Friday. Welcome to chemistry class. Today, we're jumping right back into atomic theory. We're trying to figure out what atoms are made of and what type of discoveries helped us to understand how atoms work and what those electron configurations are. Now, last class, we had a little bit of fun with iClicker. It wasn't quite cooperating. I have great hopes for today. It usually works just fine. But right after class, I opened up the word cloud, and of course, it loaded perfectly for me. So I wanted to show you the things that people were excited about their experience at Western. So top vote was for the campus. It is a gorgeous campus, and I hope you were able to enjoy the area during your orientation week. Another popular response was the people here. You're going to meet amazing people here at Western. Your roommates, your classmates, your floor mates, people in your lab, hopefully your instructors, your TAs, all of us make Western an amazing place to work and learn. Reminder, that assignment on admin matters, that OWL quiz is due. So make sure you get that in. You have a couple attempts. Make sure you meet that threshold so that you can get your 1 out of 1. The resource room is starting today. You can catch the last hour of it if you wish. So it's upstairs 1 level over in the chemistry building. If you want to see it, I can walk you over after class as I head over to my office and to my next class. I'm hearing lots of conversations, so I'm going to give you 5 seconds to wrap them up. And 1. Thank you. Those little side conversations amplify when we have a lot of people in the room. Thank you. So we have some amazing teaching assistants for our course. And almost every day of the week, starting today and moving on to next week, one of our teaching assistants, or sometimes multiple, are going to be available in the resource room just outside of the first year chem labs, ready to chat about Chem 1301A course topics. Maybe those practice problems that you started, or something we discussed in class. So here are your amazing teaching assistants. We have Katarina, Jessie, Mila, Marco, and Evelyn. They're going to have a little sign that matches our workbook. You're welcome to go up, introduce yourself, and have a conversation about chemistry. If you want to find the schedule, it's available under Content, Resource Room. This is today. We have our first kickoff session, and then you can take it from there. Okay, so let's get right back to where we were. Last class, we just started to introduce the idea of an emission spectrum, but we didn't discuss why we have an emission spectrum, what it means, how we interpret it. We just introduced this cool buzzing instrument where we can excite something and it gives off light. Light from the sun is broad spectrum, full spectrum. The light from the sun includes all the colors of the rainbow. However, people and physicists and scientists were analyzing the spectra, the light that's coming out of different elements from the periodic table. And people discovered that the light coming from hydrogen, if you take hydrogen gas and you excite it, I'm going to make sure I plug in the right one here. Here I have a glass tube of hydrogen gas. I've plugged it in to the wall. If I turn out the lights, we get this really cool pink color happening here. If we shine this through a prism, it splits the light into discrete lines. Every element on the periodic table gives its own emission spectrum. Here I have another element. Anyone want to guess what this one is based on its color? Anybody recognize this one? Go ahead and shout it out. Neon, that's correct. This one is neon. So what we have here are tubes of gas. We've applied a high voltage and something has happened. It's given us an emission spectrum. The emission spectrum of hydrogen, when we send it through a prism, splits into these discrete lines. We get a line at 656 nanometers, 486 nanometers, and so on. If you take a tube of hydrogen gas, Today, 100 years ago, on the other side of the world, it's going to give you the exact same emission lines, the same photons being released that have particular wavelength, a particular frequency, and as we saw last class, light waves have a wavelength and a frequency, and they also have an energy. We can think of light also like a particle. It's called a photon, and it has a particular energy. This is the hydrogen emission spectrum. That's the one that we just saw. I just showed you neon as well, but our eyes are not able to differentiate and separate the different wavelengths of color. We just get like an overall perception. It's purple, it's red, it's pink, whatever. But if we have a prism and a detector, a special detector that can detect visible light and measure which wavelength is coming at it, neon gives a different emission spectrum. It has different lines. It's emitting light. It's giving off photons at different energy values. And then if you look at iron, it has its own unique spectrum as well. Every element on the periodic table has its own unique emission spectrum. It produces discrete lines of color, not like the broad spectrum that we get from the sun. Scientists can identify what elements are in stars and other things in outer space based on the emission lines, based on the light that's coming from them. We can put it through a prism, identify those lines, and we can figure out that helium, for example, is in our sun and in stars. So what does this mean? Well, at the time, scientists didn't know. Last class we stopped here, but we just had a little snippet. This is where we're going to pick up today. So the Balmer series, the series that we were just looking at, the hydrogen emission spectrum that has those 4 colored lines in the visible part of the region. It actually has more lines than just those 4, but then it goes out of the visible region, so people didn't see it with their eyes originally. So Balmer was investigating these 4 lines that he could detect in the visible part of the region. And he came up with a mathematical formula that was able to predict what these lines were. And that's interesting. Okay, so there's a mathematical formula. It's consistent around the world. Something's happening, but we don't know what. Well, Johannes Rydberg was also investigating these emission lines and some emission lines from other elements of the periodic table. And he also was able to look at Balmer's formula, and Rydberg came up with an even more complete formula. And he said, you know what, I can calculate all 4 of those visible photons, those light wavelengths, using this formula here. I can calculate what that wavelength is right here by using N and M and a constant number that's big, and we call it the Rydberg constant. It was just a number. Well, if N is equal to 2, if N and M are positive integers, and for the Balmer series, if N equals 2, and then we're going to add another rule, Rydberg added another rule, M has to be bigger than N. So if N equals 2, M could be 3 or 4 or 5 and so on, 6, 7, 8. And you can actually do this, and then you'll be able to do this in your team module. You can calculate what those wavelengths are based on M and N if N equals 2. So mathematically we can do something with it. What does it mean? We still had no idea. Well, this is the visible part of the spectrum. As science develops, as instruments develop, as cool scientists and engineers develop new instruments to be able to explore further, more discoveries are made. We only had visible light detectors, but in like 1906, give or take, Lyman was able to use an ultraviolet light detector. And he also plugged in hydrogen to a voltage source, measured of light coming from it, but this time rather than looking in the visible region, he looked in the ultraviolet region, and he found more discrete lines in the ultraviolet region. And it mapped onto Rydberg's formula Because if n was equal to 1, m has to be bigger than n, so m could be 2 or 3 or 4 or so on. You could calculate what those UV photons were, what those wavelengths were of light. So cool. Well, it didn't take long for scientists to say, well, if we have emission in the visible and the UV, what if we go the other way to the lower energy region, to the infrared region? And lo and behold, Paschen did that experiment and found out, yes, we do have emission lines also coming from this same hydrogen. If we have a detector in the IR region, we can measure them, we can find them. And they had very particular wavelengths. And lo and behold, they also matched Rydberg's formula that had been published earlier. If n equals 3, m has to be bigger. So m could be 4 or 5 or 6 and blah, blah, blah. All of these wavelengths could be detected. So something's happening, something cool, but what did it mean? We still didn't have a story to explain it. Enter Niels Bohr. Niels Bohr put together a theory. He put together the story, the explanation to make sense of these cool mathematical formulas, experimental observations, tied them together into a cool story, and gave an explanation of what's happening at the atomic level. So Niels Bohr proposed, you know what? These electrons, I think, exist in orbits or little shells. So at this point, they knew they had the nucleus, positive. They knew they had electrons, negative. And they weren't just all over the place, but there was some type of order, something rational happening. So Bohr proposed these electrons are orbiting the nucleus. There is a shell 1 closest to the nucleus, and a shell 2 further from the nucleus, and a shell 3, and a shell 4, and a shell 5, and as you go out, these shells get bigger and the energy gets bigger. He proposed that you could calculate the energy of the electron, whether it's in shell 1 or shell 3, with this formula. Now the formula has a negative sign, so how does the energy get bigger? Well, he defined the electron being as far away from the nucleus where it's not attracted anymore, that's 0, and it became more negative as you became closer. So that was just his point of reference, but the energy gets greater as we move away. So what does that mean? Well, he said, I propose that the electron is orbiting the nucleus, and then it gets excited, it absorbs energy, and then when it comes back to a lower energy level, that energy is emitted in the form of a photon. I would like 2 people to help me with a demonstration who don't mind being an electron and a photon. I see you right there. Come on up. And you can come on up as well. Thank you. I think it's helpful to visualize what's happening. You have some diagrams in your workbook. You get to be the electron. And you get to be the photon. Okay. So here we have an atom. Thank you so much for participating. And this atom is in its ground state. So here's the electron orbiting in ground state, n equals 1, shell 1. Well, I'm going to come along and I'm going to get this electron site excited. I'm going to apply voltage. Are you ready? So as soon as I apply voltage, this electron is going to get excited to a higher energy orbit. You can decide if you want to go to 2 or 3 or 4 or whatever. Ready? Set, go. So now it's excited. It has absorbed this energy. It is not stable. It is really excited and it can't stay like this forever. It needs to return to a lower state. Maybe all the way down, but at least something. Okay, you're going to go to a lower state. We need this photon ready. It has just absorbed energy. It's about to give off energy. When it comes lower, this energy is going to escape, and that's you. You're the photon that's going to escape. So when you escape, you turn into a photon and then that way. Ready? So it's going to now relax. Okay, relax to a lower energy level. And now that energy escapes as a photon. Woot, woot. Well done. Okay, let's do it once more. Come on back. Okay, so you're going to stay here and be ready to be a photon. Okay, we zapped you with voltage. We could have zapped you with a photon as well. So this time I'm going to zap you with a photon of a particular energy that has just the right amount of energy to kick you from, let's say you're in level 2 and we're going to go to level 3. Okay, are you ready? So I have just enough energy, boom, and now you're excited, you've absorbed that energy. You can't stay like that forever. You are now going to give off that energy in the term of a photon. Ready, set, go. Lower energy, and now you get to run that way. Oh, whichever way, there you go. Well done. Okay, give them a hand. Thank you, and I have a treat for you if you want to. Come on over here. Okay, for participating, you can have a little treat too. Thank you.
Thank you.
Thank you. Awesome, okay. Bohr proposed this is what is happening. He also proposed a formula, and the formula matched the experimental observations. The energy can be absorbed, that excites the electron, but then the energy can be released, and that's a photon coming off. That energy is being emitted in the form of a photon, which produces an emission spectrum. We can calculate the difference in energy between level M, the bigger one, and N, the lower one. Maybe it's 3 to 2, or 2 to 1, or 5 to 3, whatever, bigger number to smaller number. That difference in energy is this formula that you see here. If we factor out the h and the c, those are just the speed of light, and I think that's Planck's constant, a tiny number, we end up with Rydberg's formula, the one that Rydberg proposed that could calculate all these wavelengths. What does this mean? Well, this is the delta E, the change in energy from a higher energy to a lower energy, and this is equal to the energy of the photon that is released. You can calculate the energy of every emission line, and it matches the energy difference between these different shells where Bohr proposed the electrons were orbiting. So either a photon comes in or voltage is applied, it gets excited, and then when it comes down from a higher energy level to a lower energy level, that energy is emitted. The energy that is emitted comes out as a photon. The energy of that photon matches the difference in energy between those shells. Let's look at this Balmer series once more. The Balmer series, we know, is in the visible part of the spectrum. For example, 656 nanometers or 486 nanometers. Looking at this Balmer series with the 4 lines that are part of the visible region, and again, it continues on, it just goes past what our eyes can see. Which of these 4 emission lines has the smallest energy? Chat with the person beside you for 10 seconds. Which of these 4 colors has the lowest energy? Okay, and hands up. Who says it is the purple line, lowest energy? Who says it's the red line, lowest energy? Okay, I agree. That is the lowest energy. Well, for the Balmer series, n equals 2. That means it's all coming back to level 2. It could be coming from level 3 to 2, or 4 down to 2, or 5 down to 2, and so on, but it's coming down to level 2. That's how we produce these lines. Well, which of these transitions produced the red line, the one that has the lowest energy? Chat with the person beside you for 10 seconds. Which transition produced that line? You want to say? Oh, we got a question. Okay.
So when all of it comes out of light?
Sometimes it could. Right now, no. Yeah. Okay, and 3, 2, and 1. Okay, hands up. Who says it's energy level 3 to 2 that produces the red light? Okay, and you are correct. This is the smallest energy transition that's happening. It's the smallest gap, so that matches the lowest energy. If we go up a little bit, the 4 to 2, well, that's going to be the next one, and so on. Higher energy photons mean bigger energy jumps. Okay, so now I have a slightly complicated iClicker question for you. I would like you to chat with the person beside you. Based on Bohr's model, which of these electron transitions produces the highest energy photon, the emission line that has the greatest energy? Chat with the person beside you, and you can look at this image as well. And 10 more seconds to get your answer in. And 3, 2, and 1. Okay, well done. Most people went for C, and I agree. So 3/4 of you got to that answer. Well done. How did we figure that out? Does anyone want to give an explanation for how they chose C? Yes. Can you pass the microphone there, please? Thanks.
So we went with C because we know UV light has, it has more energy than infrared light when we look at the spectrum, as well as we can look at that difference being 3 to 1, which is bigger than 2 to 1. So that difference of 2 is another factor in why that has the highest energy photon.
Excellent. Very good explanation. Well done. Okay, I don't think I have anything to add there. We were able to narrow it down. UV versus IR. UV is the higher energy. 3 to 1 transition versus 2 to 1 transition. A 3 to 1 is a bigger energy difference. Another consideration is that, and I don't think I've specifically mentioned this, as we go out, the shells get closer together, and that matches Bohr's formula that he predicted. So level 1 to level 2, and then they kind of get closer together. The 3, 4, 5, 6, 7, they get closer and closer, which matches Bohr's formula. It matches the picture here, but maybe you didn't notice that yet. So the energy transitions that we're seeing in the ultraviolet region are much larger compared to the smaller jumps that we have in the infrared or passion series. So well done. I thought that was a tricky question, but it didn't trick you, so well done. Not that I try to trick you. It was a complicated question and you thought through it. Well done. Okay, so that means we solved the atom and we can all go home, have an amazing weekend. Don't go home yet. I still want you to have an amazing weekend. But they thought they had solved the atom. Hooray, we understand that electrons are orbiting, and now we can explain the hydrogen emission spectrum. We know where the electrons are, what they're doing, and it matches the energy, and it matches our experimental results. Awesome, we're done. We don't need to develop any more theories about electrons and atoms. Except there were some deficiencies. This model didn't fully explain all the experimental observations. It didn't fully explain some very important questions. For example, why does the electron stay in energy level 1 and not crash into the nucleus? It's a negative and a positive. Why don't they just attract and collapse and the whole world collapses? Why is there an energy level 1 and an energy level 2 and an energy level 3, but not an energy level 2.5 or 3.25? Why can they only be positive integers? And as instruments developed, as the resolution developed, they discovered, you know that 656 nanometer emission line, that photon, the red one? If you zoom in with a better instrument, it's actually a split line. It's actually two lines. That doesn't match Bohr's explanation. Having split lines, we don't have an explanation for that. And why doesn't this work for electrons with more than one electron in its valence shell? It works for hydrogen, that's great. What about iron? What about neon? You didn't map on. This theory was a great theory. It helped to expand and develop our understanding of the atom. We still teach this theory in elementary school and high school. It still gives you a basic understanding of electrons in inner shells and outer shells, lower energy and high energy, but it's not actually fully accurate. It's not complete. Electrons don't actually orbit the nucleus. It's a nice idea, but it's too simple. It's not actually what's happening. The electrons are doing something way more complex. How do we figure out what's going on? Well, we need some quantum mechanics to help us figure it out. So, for understanding quantum mechanics, we need to do just a little bit more physics. We need to understand what waves are again. Now, at the beginning, last class, we talked about how light waves have a wavelength and a frequency and a speed. So light waves are a wave, and that is true. But light waves we can also think of as a little particle, a little packet of energy that we can throw somewhere. So light is a wave, but light as a photon is kind of like a particle, and Einstein and Planck proposed that light is kind of like a particle too. Well, what if matter? What if stuff? What if electrons? We know they're particles. They have a tiny little mass. They have a charge. It's a particle. But what if electrons also behaved like waves? What if they also had wave-like properties? And this blew everyone's mind, and it finally helped us to understand electrons and atoms. So if an electron could behave like a wave, how would we know? Well, we need a few more details about waves. We know waves have wavelengths, frequency, energy, but they also do a few more things. Waves can undergo diffraction. That means if we're shining a light at a wall and there's a tiny little pinprick, it's going to go through the hole and then it expands out. It diffracts. It fills up the space on the other side. Light does that. Particles don't do that. So they diffract. They fill up the space. Waves can also undergo interference. They interfere with one another. They get in each other's space and impact one another. They can impact each other in constructive ways or destructive waves. So here in part A, I have two waves, and they're in phase. They're both going up at the same time and down at the same time. The wave on the top starts by going up. The wave on the bottom starts by going up. We can add these waves together. Remember your vectors from math class? The up and the up get added together, and the down and the down get added together. And this is constructive interference. You can imagine you're feeling happy, your roommate's feeling happy. Add that together and you just both feel amazing, right? Constructively building on each other's emotions. Or you come back, you're happy, and your roommate's sad. And you kind of destructively add together. Your happiness and their sadness kind of turns into just a mellow evening. So destructive interference is when one is going up, one is going down. We could call this out of phase. They're not going up and down at the same time. So now we have an up vector at the same time in space as a down vector, and that adds to a vector of 0. And then we have a down, and then we have an up, and meh, they both mellow out at a 0. Waves do this. Matter, stuff, doesn't do this, at least on the micro scale. So if we wanted to figure out if electrons, for example, were particles, we already know they're particles, or if potentially they have wave-like properties, maybe we could do some experiments and theorize and figure it out and find out if that's actually what's going on. Enter the double slit experiment. Hands up, you remember this phrase from high school, the double slit experiment. Awesome. So this should be review for many of you. If not, hang on, you'll get a nice explanation. Okay, if we have light waves coming in, and there are 2 tiny little holes about the size of the wavelength of light. It can't be a massive hole or, not a hole. It has to be proportional. It has to be a tiny little hole. Well, as the light passes through that hole, it diffracts. It fills up the space on the other side of the hole. And the light coming through the second hole also diffracts and fills up the space. And when they interact constructively, we can add those maximum together to make an even bigger wave. And when they add destructively, they add together and make no wave or a dark spot. Now, these are light waves. I think it's helpful if we look at some mechanical waves, because those ones are just a little bit easier to visualize. So here we have an example of the double slit experiment, but we're using water waves. Okay? Water waves travel outwards. They're called traveling waves, but it still gives us an idea of constructive and destructive interference.
Wave fronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up, peaks and troughs, the amplitude of the wave is increased. That's what we call constructive interference.
Okay, so I'm going to pause there for just a second. Who's thrown a rock into the water before? Okay, so we can all visualize. We throw the rock in, and then it goes plop, 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 and it propagates waves outwards, right? If you do like a cannonball competition, you propagate waves outwards. Well, if we have 2 sources making waves at the same time, 2 people doing cannonballs into the pool at the same time, those waves can interact. And here we can see visually the waves interacting constructively, where you see the bigger waves, and destructively, where it's nice and calm, where the maxima and minima were added together, out of phase, destructive interference. And it looks flat if we're looking at like a physical water wave. In terms of light, it looks dark. So the brighter spots, constructive interference, the darker spots, destructive interference. Okay, so that's how light would behave. How would particles behave if they were doing a double slit experiment? Well, let's imagine that these are my electrons. And let's imagine I broke the glass, but I'm not going to because I get in trouble. Let's imagine that this is a slit. And I have electrons, and I'm just going to bombard these electrons at the slit. Now, if I miss the window, it's not going to go through. It just throws back at me, as you saw. But if I hit the window directly, it's going to continue right through and hit someone on the other side, right? We would expect particles to either be deflected or to go straight through. Particles would make bright spots or hit in those 2 regions that match where the hole is. In contrast, electrons are going to make this cool diffraction pattern with constructive and destructive interference. Well, before scientists actually did this double slit experiment, de Broglie proposed this revolutionary idea that electrons behaved like waves. And this was called wave-particle duality. We know they behave like particles, but could they also behave like waves? And de Broglie proposed this revolutionary idea, blew everyone's minds, that electrons, that stuff, matter, could actually behave like a wave as well. And he did this by proposing this rather unique formula, saying that mass could be related to wavelength. Now for light doesn't have a mass. It has a wavelength and a frequency. Light does not have a mass, but electrons do have a mass. If the mass is really, 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 really tiny, we could actually find a way to measure its wavelength. And it really kind of only works for electrons and really, really, really tiny microscopic things. Planck's constant is very small, something times 10 to the negative 34. So that mass is also going to need to be really small. He was able to say, I'm relating mass to wavelength and velocity, and now stuff could have wave-like properties. Now he proposed that idea before he had experimental evidence of a double slit experiment to back it up. But the cool thing is, a few years later, scientists were able to do a related experiment with a crystal and X-rays and actually produce a diffraction pattern from the electrons. A few years after that, they were able to do an official double slit experiment, come up with a beam of electrons, and again, it did produce the diffraction pattern. These experiments confirmed de Broglie's really revolutionary hypothesis that electrons can also behave like waves, which is pretty cool. So if we want to understand electrons, that means we need to understand waves. Now we've heard about traveling waves already. We saw traveling waves in the video. You throw a rock in the water and the wave propagates outwards. That's a traveling wave. If you're hearing my voice right now, you're also hearing a traveling wave, but it's like a physical wave where the particles are hitting each other and making patterns in your ear, which is being translated to your brain. Those are traveling waves. But electrons behave like standing waves. Now I need a volunteer to come help me hold the slinky, come on down, and turn this slinky into a standing wave. Thank you, come on down. Okay, so you get to hold this side here. Yes, okay, so you are an anchor point and I am an anchor point. Standing waves, here, let's come this way for a second. Standing waves are bound. They can't just travel over to Einstein's and get a coffee. They are bound. They're locked in there and they're locked in here. Now this wave, you hold still, and I'm going to try to get this wave to go up and down. Now this is one way that the standing wave can have a nice pattern. See how it has above phase and below phase? It's above where our hands are and below. That'd be positive phase, negative phase, positive phase, negative phase. And it has this nice repeated pattern. And this is one way that I can make my slinky move. Now I'm going to do something here. Now I have the next energy level. I'm trying to just go straight up and down. It's trying to turn into three-dimensional, and I'm just wanting to show one-dimensional. Two. So now, I have a volunteer maybe in the front. Come show me where the node is. Okay, come on down. So here, I have another way that it's maintaining its pattern reasonably. And this time it has a node. And this volunteer is going to show us where the node is. Where is it not moving? Awesome. Okay, does everyone see where that node is? Thank you very much. Okay, now I'm going to work a little harder and see if I can get it to do 2 nodes. Okay, do we have 2? Thumbs up, can you see 2? Can I get to 3? See how hard I'm having to work now? As we increase the number of nodes, this slinky is increasing in energy. Okay, give a round of applause to our slinky. Thank you. And the node. And both of you can come see me after class if you want to get a little treat for volunteering. Okay, we just saw a standing wave. It is anchored on both ends. The anchors on the ends we don't consider nodes, so we're not going to count those spots, okay? The anchors are just holding places. So there's option number 1. lowest energy. Option number 2, again, it's anchored, but this time it has a node, a little region where it's not going up or down. And if I worked even harder, I could get 2 nodes happening there now. So 1 versus 1, 2. As we go up, increasing the number of nodes, we increase the energy. And lo and behold, wave properties apply to electrons. We can describe electrons as though they are standing waves. Electrons can be described by a wave function. And we use this little psi symbol, and I saw that on many of your t-shirts. Did you have a psi symbol this year on your OEs? Okay, so you're familiar with the psi symbol. That represents a wave function. And we use wave functions to talk about electrons. And not to confuse you, I'm probably going to be using those words interchangeably. I could talk about a wave function, I could talk about an electron. The wave function describes the electron. So I could say a wave function or an electron is at this lowest energy level. And it has some type of consistent pattern with no nodes. Or I could increase in energy and have another way, wave function 2, to talk about that electron, but this time it has a node. Or I could have another wave function to describe that electron. The number of nodes has increased again, and now it has 2 nodes. I can actually calculate the number of nodes by saying energy level 1, 2, and 3 minus 1, and you get the number of nodes at that energy level. Now here, we're talking about the wave function in dimension x. So we're only talking about like one-dimensional waves, but waves actually exist in 3 dimensions. We don't give you a 3-dimensional wave because it's really hard to draw, and we don't have a really good way of showing that yet. So we're going to talk about the 1 dimension and keep it nice and simple. As I say, we're going to keep it nice and simple. I'm going to put this amazing formula on the screen. Here, we have the Schrodinger's equation. Hands up if you have heard of Schrodinger's equation. Hands up if you have heard of Schrodinger's cat before. Okay, the idea with Schrodinger's cat is it's this thought experiment. If we had a cat in the box and we had a potential nuclear decay about to happen, there's a 50% chance that it's going to decay and break and kill the cat. There's a 50% chance that it's not going to decay and it's not going to kill the cat. But as soon as you open the box, you've killed the cat. So we don't know if the cat is dead or alive. Is it dead and alive? Is it both? We don't know. And that kind of applies to Schrodinger's equation. Schrodinger's equation allows us to do something really cool. It allows us to figure out the energy of an electron and describe its size and shape. And that's what the rest of the formula, or that's what this psi is helping us to figure out. The psi is helping us to figure out its size and shape, and we can have a way to connect that to energy. Once you know its energy, you don't know its size or shape. Once you know its size or shape, you don't know its energy. Once you know exactly where that electron is, you don't know where its energy is. If you know its energy, you don't know exactly where that electron is. What this gives us instead is a set of probability values. And we're like, that's good enough. As long as we have, 90% chance it's somewhere in this region and it's never there, we're good with that. So it doesn't give us the full answer at this specific moment, but we know majority of the time it's in this region. Now, this formula is really cool to solve. When I was in my second year quantum mechanics class, we were able to use this formula to talk about a 1-electron system with hydrogen, solve it, and it was, it could be simplified. We did the simple version, and we were able to figure out the wavelengths in the Balmer series, match the energy of those photons and figure out the energy of the electrons using this formula. It's very cool, but you're welcome. We are not going to solve Schrodinger's equation. We're going to say thank you very much to the previous scientists who already did the hard work for us. We are just going to interpret the solutions. And I did say plural on that answer. There are multiple solutions to the Schrodinger equation. So for our class, we get to say, wow, that's an amazing formula. It helped us to figure out what electrons are doing. It solved a whole new layer of chemistry, but we're just going to say thank you, and we'll just work with the solutions. We can figure out energy. We can figure out shape and size. If we take the square of that psi function, we take the square of the wave function, it tells us the probability of finding an electron in that region. So we could say, oh, there's a 90% chance of finding it in this sphere. There's a 90% chance of finding it in this dumbbell. And that is good enough for us. How do we interpret the details of the Schrodinger's equation and what those solutions mean? Well, they're interpreted using quantum numbers. But that's a whole other topic for next week. So we're going to wrap it up there. Have a fabulous weekend, and I'll see you on Monday.